Do it. Let me get a drink first. Here, I'll mute it so you don't have to listen to me. Okay. Now it's going to get real. This topic, including lower level predictors, is where 95% of mistakes are made in the multi-level model. Okay. They are complex. And we're going to walk through some of this complexity. And again, if it doesn't, I struggle when I'm not that far removed. I'm like 12 years removed from learning this stuff for the first time. And I remember the frustration I had while I was going through. Be patient with yourself if you're not getting it right away. And then in the example, all interpretations are provided. So again, you can lean heavily on those interpretations as we go through, okay? But this really is the meat of where I wanted to go with this workshop. Okay. So part 7 of 12, adding level 1 person level predictors to the multi-level model. So the joy, that's sarcasm, of level 1 predictors, they're complicated. They're complicated because they generally represent an aggregate effect of 2 sources of variance. There's between group variance. Some groups just have more of the predictor than other groups. There's also within groups. Some people within a group have more of the predictor than people in their group. If we want to map this directly onto something like age, some people live in states where the folks are just older. I'm looking at you, Florida. I am older than some people in my state. That's a within group. Okay. This is conceptually identical to what we were doing with our disability outcome. Some states had more disability, or higher disability scores than other states. Some people within the states had higher disability scores than others in their state. What does that mean? We can actually, for every single level 1 predictor, we can actually quantify how much of the variability is at the between state or level 2 level. And we do that the exact same way we had done previously with our intra-class correlation. We're literally going to dump our level 1 predictor into that unconditional empty means random intercept model, unconditional random intercept model. We're going to treat our level 1 predictor as the outcome, and we're going to calculate our intra-class correlation. If the ICC is greater than 0, it has between group variation. If it's less than 1, it has within group variation. Okay. So if we consider students nested within schools, and we're looking at socioeconomic status with an outcome of achievement. At the between school level, schools with more rich kids probably have greater mean achievement than schools with more poor kids or less rich kids. I think that's been shown repeatedly. Within group, rich kids in a school may have higher achievement than less rich kids in that same school. Okay. We're dealing with one SES indicator, though, okay, that we're going to basically have to brute force partition into its level 1 and level 2 components, and we're going to see that going through here. The partitions we're talking about can actually have different scales at different levels as well. So if at level 1, we're talking about, let's say, student biological sex, male versus female. At level 2, we could have the school percent of female students. So we have a binary variable at level 1 and something continuous-ish at level 2. It's bounded, so it's not truly continuous, but it's something between 0 and 100. There are 2 centering options to disaggregate level 1 effects from their level 2 components. There's grand mean centering and there's group mean centering. I'm going to cover grand mean centering first because that is generally of more interest in clustered models. I'm going to cover group mean centering second because it is less interesting in clustered models. But no, if you work with longitudinal data, grand mean centering still exists. Group mean centering is going to be called person mean centering. for longitudinal data, group mean or person mean centering is going to be more useful to you than grand mean centering. Okay. You have to understand both of these, and you have to understand how this centering is actually occurring, because your centering choice is going to dictate interpretations at level 2. So let's consider people clustered within states and a level 1 predictor of age. There is a level 2 between group effect of age. That is going to be represented by the state's mean age. So the average age of people living in that state. There's a number of ways to obtain that information. If you're using data that is from some sort of stratified random sample, you can actually take the average of the age across all individuals in that state for those who responded in your data set. That's what we're going to do here. Okay. So for each state, I'm going to take the average age of every single respondent to the American Community Survey and find the average age for that state. Each state is going to have something of a different mean age, and it's going to be constant within a state. The other way to do that is to use census data and just incorporate that as well. You can run into hiccups with that, though, and we'll talk about that related to the correlation within the data. We'll talk about that here in a minute. But again, what we're going to do for our example is we're going to take the average age of respondents within the state they're in. So our average state age is not the actual average state age. It's based on our sample data. We're then going to center it like we do with every other predictor. We're going to center it at 65. So state mean age 65 is our average state age centered at 65. So a value of 0 on that predictor equals 65 years of age. What happens at level 1 is actually where this centering comes in. And I saw a question in the chat about centering, and I'm hoping this section will answer that question directly. If it doesn't, let me know. At level 1, our within group effect of age is going to be based on our centering choice. If we're using grand mean centering, we're going to center at some constant value. So previously in the code, I jumped ahead of myself there. I centered age at 65. So I took each respondent's age and subtracted off 65. What that means is that because I've subtracted off a constant, all I've done is shifted that distribution. That age variable likely still contains level 1 and level 2 variability. We're going to see how much variability is in there once we calculate the ICC for it in the example. Okay. So if we're using grand mean centering, it means we're subtracting off a constant value. It does not need to be the grand mean. Again, that's a bit of a misnomer. It just means we're subtracting off a constant from every single observation in our data. Because we're just subtracting off a constant, we're not doing anything with the level 1 and level 2 partition. That level 1 variable still contains between state variability. Again, it is likely that some states just have older respondents compared to other states.
Ryan, we've got a question. I'm sorry to interrupt you. We've got a question. So it says, can you ask, she's referring this to me, can I ask you if there's an example for applying the multi-level model to dyads?
Yes, I don't have an example for that. There is a lot of literature and there's a lot of examples out there for applying it to dyads. I would recommend you picking up Lisa Hoffman's book. I think it's called Longitudinal Data Analysis. I actually have a list of readings and texts that you could purchase that was provided as a PDF as well with the workshop requirements. Dyadic data, though, given that there's only the dyads by definition include 2 observations at the higher level, they're actually better modeled using truly multivariate methods, not necessarily a standard multi-level model, because again, you need at least 3 observations to truly calculate a variance, and a dyad doesn't meet that requirement. There's a lot of methods work out there. There's a lot of examples out there. I do believe Lisa Hoffman's textbook speaks to that. I hope that helps.
Great, thank you.
Yep. Okay. So again, grand mean centering is going to retain level 1 and level 2 variability within that level 1 predictor. In contrast, group mean centering is going to be where you're actually going to center your level 1 predictor variable at the group specific mean. So this is what we call variable centering. You're centering at a variable that is constant for all people within the same group, but likely differs from group to group. This is what we're going to call within state age. We're going to take the observed age and we're going to subtract off that respondent's state's mean. Okay. What you can see here. So if age contains level 1 and level 2 variability, and state mean age only contains level 2 variability, what we are actually doing conceptually is we are subtracting off all of the level 2 piece from this variable. So this within state age variable only represents a level 1 effect. Because again, we've subtracted off all of the reason the states are different. We're going to talk about grand mean centering first with lots of examples. And if there's time, which I hope there will be, we're going to talk about group mean centering. Again, the interpretation of the level 2 fixed effect, of the level 1, level 2 fixed effects is going to differ depending on your centering decision. And the differences in interpretations are going to be shown here. So level 1 predictors contain 3 different effects. A single level 1 predictor contains 3 effects within it. It has a level 1 within group effect. So do you have higher predictor values than others in your group? If you do, are your outcomes higher or lower? Okay. Level 1 effects explain level 1 residual variance. Level 1 effect, again, is at the person level. Residual variance also at the person level. Okay. The confusion comes in with this because there's 2 different types of level 2 effects. The first one is a truly between group effect. So do groups who average higher predictor values compared to other groups also average higher outcome values? This is a level 2 effect. This is going to explain level 2 random intercept variance. The effect you may not have heard about prior to this is what we call the contextual effect. This is also at level 2. The contextual effect has 2 specific definitions. Both of them are important. The first is related directly to that fixed effect. So after controlling for the level 1 predictor for each person, is there some sort of an incremental contribution of having to the outcome of having higher predictor values compared to other groups? So still a level 2 thing. The contextual effect also is an explicit test of whether the between group effect and within group effect differ. Okay. So you can interpret the fixed effect directly, but you can also test whether this between group effect and within group effect differ. When I said earlier that 95% of people estimating multi-level model, again, that's the confidence interval around that would probably range from 20 to 100%. Either way, 95% of the mistakes I see in the multi-level model are when people dump level 1 predictors into the model by themselves without accounting for the fact that that level 1 predictor contains level 2 variability within it. When you include a level 1 predictor in the model by itself, you are basically assuming that the between group and within group effect are equal. That's implicit running in the background. This is termed convergence. So convergence is a word I'm going to use repeatedly. Convergence effects are bad if they're not tested directly. Okay. And the convergence effect, assuming the level 2 and level 1 effects are equal, is an explicit empirical question that can be answered by the contextual effects asking if they differ. We're going to get a p-value for that, an actual statistical test of whether they're different. So you don't just have to assume convergence, you can test it and then have more information on how to move forward with your model. The hiccup in this, I guess the additional hiccup in this is that whether you use grand mean centering or group mean centering, those centering decisions are only going to give you 2 of those 3 effects. Grand mean centering is going to give you within and contextual. Group mean centering is going to give you within and between. And I have this explicitly shown going forward, okay? You'll have to request the 3rd, and I'll show you how to do that as well. So let's talk about grand mean centering. So we're going to consider age 65. So again, age centered at 65 for each person. Why not just include this predictor in the model by itself. We're going to see in the example that this age variable has between and within variation. Because it contains level 1 and level 2 variation, between and within variation within it, this fixed effect for age is actually a combined effect of the between and within group. It's not a pure within group effect. It's not a pure between group effect. It's a weighted combination of those two effects. So it's somewhere in the middle. Either way, it is not what you think it is. Okay. Most people throw level 1 predictors in the model. They think they're getting level 1 effects. When you do that by itself, you are not getting a level 1 effect. Okay. You're getting some weighted combination of its between and within partitions. Know that this fixed effect, though, is going to be weighted more heavily towards level 1 because that's where more data is at. You can see that clearly in our example because we had 400,000 and change observations at level 1 and only 50 at level 2. That's an extreme example. I've seen multi-level models where they have, 10 level 2 units with, let's say, 3 or 4 at level 1. So then the differences they get a little bit closer together, but it's always going to be weighted more heavily towards level 1 simply because there's just more information there. Okay. Including this predictor in the model by itself, again, assumed convergence, that the level 1 and level 2 effects are equal. This is testable again via the contextual effect. Depending on who you're reading, they'll call it convergence, they'll call it conflated, they'll call it composite, they'll call it smushed. They're all synonyms for the same thing. You're getting some sort of combination, weighted combination, that isn't a level 1 effect like you want it to be. Why is that? I can show this in pictures as well. So we took our disability outcome and we actually separated out between state variability and from within state variability. When we did that, we did it using model-based methods via the random intercept. Random intercept captured the between group differences in disability, leaving within group differences as the residual. That again was a model-based partitioning. What we've actually done by including that level 1 predictor by itself is we've asked one predictor to do the exact same thing, and it can't because it only provides one effect. So there is a between group effect, there is a within group effect, but again, the fixed effect for that single predictor doesn't represent a pure level 1 effect. How do you know that you've done this? Again, now you know, and knowing is half the battle, I guess, as an 80s child who grew up with G.I. Joe, but knowing is half the battle. You shouldn't just include them by yourself. I'm going to show you a better way. But if you're calculating pseudo R-square, you can identify explicitly that a predictor level 1 predictor contains level 2 variability within it. Again, level 1 predictors should only explain level 1 residual variance. They should. You can calculate pseudo R-square. Again, subscript matters. So residual variance before the predictor, residual variance after the predictor, all divided by where we started from, you get a proportional reduction in variance. If that level 1 predictor also reduces level 2 random intercept variance, you know immediately that predictor contains level 2 variability within it, and you need to account for that. And the way we're going to account for that is by also including state mean age in the model as well. Again, state mean age centered at 65 is the average age of respondents within a state within our data. Within and between group effects are only estimated when both of these variables are included in the model. So we've added an additional fixed effect here. This also, again, I probably should have pointed this out earlier. Color coding here matters. Tan is for level 1 effects, gray is for contextual effects, and green is for between group effects. That color coding is going to be constant going through. So what we have here is we have age 65, which still contains between and within group variability. And then we have state mean age 65, which is only a between group portion. So now, because these two variables share a correlation, the effect of level 1 age is the unique effect after controlling for state mean age. This is a standard interpretation for any multiple regression model, multivariable regression model. After controlling for state mean age, we have the unique effect on the outcome of being 1 year older. The contextual effect, again, also controls for level 1 age. So it's the unique between group effect after controlling for a person's age. It also tests whether the within and between group effects are different. So in terms of pictures here, again, our disability outcome, random intercept variance, level 1 residual variance, originally we had our level 1 predictor that explained level 1 and level 2 variability. But once we've included that level 2 state mean age within it, this effect goes away because we've statistically controlled for it. So we end up with a level 1 effect after controlling for level 2 and a level 2 effect after controlling for level 1. So that terminology, unique effect, statistically control effect, matters. Why are we requiring statistical control? It's because the level 1 age predictor and grand mean centering still maintains a level 2 piece within it. This is conceptually identical to a garden variety linear regression model. If we have two predictors, X1 and X2, if they share some correlation, the fixed effect of X1 is the unique effect after controlling for X2. The fixed effect of X2 is the unique effect after controlling for X1. That's the exact same rationale we have here. So group or grand mean centering provides within group and contextual effects, which means at level 1, we have a unique effect after controlling for level 2. And at level 2, we have a unique effect after controlling for level 1. So again, I'm belaboring this point intentionally because I want the interpretations to stick, and the example should help with some of this as well. So grand mean centering is likely more useful for cluster data because people generally care about contextual effects. They want to know what happens at the state level after controlling for the people within a state, right? Grand mean centering is going to give you within and contextual. That third effect, that pure between group effect, is not estimated directly, but you can ask for it. The between group effect is calculated as the sum of contextual and within. So if you take the contextual effect and add it to with the within group effect, you're going to get the between group effect. You can do this directly from the same model you've estimated in Stata using LinCom statements, in SAS using estimate statements, in SPSS using test statements, and in R following Lemur using contrast 1D. If you use LME4, it's the multcomp package that will allow you to do those post hoc type estimate statements. Okay. Alternatively, you could use group mean centering, and we'll get there in a second. So grand mean centering, all you're doing is shifting the level 2, or the level 1 variable, moving it around by a constant. You're not doing anything to remove the level 2 component of the level 1 predictor until you also include the level 2 partition of that predictor in the model as well. And then you're statistically controlling for it. So with that in mind, let's go back to the example. So again, still talking about grand mean centering. We're going to look at the interim analyses for age, and we're going to look at models 3A and 3B. So I mentioned earlier, there is really no conceptual difference between a level 1 outcome like disability was, right? Every person responded with a disability response. That is actually a person level thing. So is age. So all we're doing is we're going back to what we had estimated for model 1 here in this example, and we're swapping out disability for age. So we have a fixed effect, a random intercept, and a residual variance. The first thing I want to do is I want to show you that there is correlation here. So I'm going to take this age P65 at level 1. I'm going to correlate it with all the level 2 things we're going to include in the model. Then I'm going to use the mixed statements we had seen earlier and just ask for an empty means random intercept model with age as the predictor. We're going to ask for the intra-class correlation. So all of this code you have seen before. Let me zoom in here a touch. I don't know if that's really, oh, that's right. Okay. What we're interested in is this column here. So age P65 has a correlation of 0.05 with state mean age. What that means is that age P65 at level 1 contains level 2 variability. If it did not, that correlation would be a hard 0. Okay, so non-zero correlation indicates there's a problem. You can also see that it's correlated to a lesser extent with unemployment and right to work. So age contains level 2 variability. Level 1 age contains level 2 variability. How much variability can be calculated with the intra-class correlation? So the random intercept variance for age is 0.8, residual variance is 256 and change. We get an ICC that is 0.31. So approximately 0.3% of the variance in age is at the state level. Again, Stata and R will give that to you directly. If I go, well, I didn't do it here. I didn't do it there. I apologize. I could add that in later. But the ICC can be calculated by pumping these values. Actually, you could pump them in right here, and it would calculate it directly for you. Okay. But what this means, so we've seen non-zero correlations, we've seen non-zero ICCs. What that means is when we include level 1 age, we have to be concerned about its level 2 partition. So the first thing we're going to do is show you an erroneous convergence effect. We're going to include level 1 age centered at 65 by itself. In the software, we're just adding it as a fixed effect in Stata, in SAS, in SPSS, and in R. Okay. Just like we had done before, we're going to output predicted values based on the fixed effects, correlate it with the observed disability outcome, and then square that correlation to get our R square. So we can see here as a fixed effect. Again, fixed effects, the statistical significance of them is dictated by p-values. So age p65. So for each additional year of age, disability scores went up by an average of 0.01. That is statistically significant. Again, p-values can't be 0, so p less than 0.001. Okay. We can look at pseudo R square. Again, statistical significance is no longer a starting point, thank goodness. We can do pseudo R square for the residual variance. Remember, level 1 predictors are supposed to only explain level 1 residual variance. How much residual variance did it explain? Compared to model 2B, it explained 2.3% of the residual variance. I mentioned earlier that you know that something went awry here because this single level 1 age predictor also explained 3%, an additional 3% of random intercept variance. This value should be 0 or negative. I mentioned earlier, again, in passing, that if you explain level 1 residual variance only, level 2 random intercept variance should go up, which means you should have had a negative pseudo R square, which was expected. Here, we actually explained 3% of random intercept variance. So this one predictor is doing the job at level 1 and level 2. So that's a problem. We know we need to do something to account for that level 2 partition. You can see here that the correlation now has increased substantially from 0.019 or something to 0.1511. Square that, that's 2.3%. So this age, so state mean unemployment, state right to work status, and person age by itself have explained 2.3% of the total variability in that disability outcome. Interpretations of your fixed effects are provided. Again, using grand mean centering, we know now that that level 1 predictor contained level 1 and level 2 variability, so we're going to statistically control for it by including state mean age. Okay. So still including age at level 1, but now we include the level 2 component with it. Still treating it as continuous, still a fixed effect. Okay, we're just adding it on the model statements here and here. So we're going to get a level 1 effect and a contextual effect. I mentioned that the between effect is not going to be given directly, so we can use LinCom estimate test or contrast 1D statements. For LinCom statements, I'll highlight these here. The within state effect of age is going to be given to us directly by HP65. So this predictor. So all we're going to do is take that fixed effect, multiply it by 1. The contextual effect is going to be given to us directly by state mean age 65. So we're going to take that fixed effect of state mean age 65 and multiply it by 1. The between state effect is not given to us directly. Remember, the between state effect in grand mean centering is within plus contextual, or contextual plus within. So we're going to take that state mean age 65 fixed effect, multiply it by 1, and add it to the level 1 age P65 effect, multiply that by 1. This is going to provide us a linear combination that is going to give us the between state effect. We're doing the same thing, a little bit different in SPSS and SAS. We're going to take our age P effect, multiply it by 1. We're going to take our state mean age effect, multiply it by 1, and then we're going to add the contextual and within effect. There's no plus signs in SAS or SPSS. The plus is implicit to the estimate statement. The estimate statements and test statements are going to give you linear combinations, sums of them. Okay. In R, it's a little bit different for the contrast 1D. We're going to define the model, and then we're going to, I believe C stands for concatenate. These are literally the effects as included in the model. So the first column here is the fixed intercept. Second column is state mean unemployment. Third column is right to work. Fourth column is age at level 1. Fifth column is state mean age. So again, within state age is given to us directly. So we're going to ask for that fixed effect only. Contextual effect is given to us directly by state mean age. We're going to ask for that fixed effect only, and then we're going to sum them together to get the between. Okay, so once we add state mean age into the model, we can see that the fixed effect is not statistically significant. So after controlling for a person's age, states that averaged 1 year older respondents averaged disability scores that were higher by 0.0039 units. So that's the interpretation of the fixed effect directly. The other interpretation of that contextual effect is whether the between and within effects differ directly. So this being not statistically significant means that the between state and within state effect of age are not statistically different, but not statistically different does not mean equal. Okay. You can see now that after we've included state mean age, we've explained 0 additional residual variance, as you would expect, because state mean age was a state level thing. And we've also basically dropped our random intercept variance back down to where it was previously. This state mean age predictor was not statistically significant, and it explained 0% of random intercept variance. The -2 log likelihood we're going to come back to here in a minute. These are the LINCOM statements we had asked from Stata. Again, within state age was given to us directly by the model, 0.011. So after controlling for state mean age, a person who's 1 year older averaged 0.0116 points higher disability. The contextual effect, again, I had interpreted earlier, is given to us by the model directly. It is not statistically significant. The between effect is within plus contextual. So if I take 0.0116 and add it to 0.0039, I get 0.0155. This between state effect is only at level 2. There's no controlling for this. So states that averaged respondents who were 1 year older average 0.015 units higher disability. That effect is not statistically significant. Okay. Again, the contextual effect tested whether the between and within state effects were statistically different. They are not, but you can see here that they're also not equal. Okay. I've seen methods literature. I've heard from the methods heads in my field, so quant psych, that because they're not equal, it should be maintained. Retain that contextual effect, retain that state mean age effect in the model to ensure that what you're interpreting at level 1 is a pure level 1 predictor. We can calculate total R squared, no different than we had previously, still explaining only 2.3% of all the variability. I want to come back here very quickly to our -2 log likelihood. Again, we're going to take our log likelihood from the model, multiply it by -2. This should be negative. Come here. Oh, come on, man. Oh, this is a PDF. Sorry. See, you want to talk about cognitive capacity. It's starting to dim. But you multiply it by -2. This is going to be the starting point for where we go next. So 1310760, that value is going to show up again. So that is from model 3B. Okay. That's going to be our comparison model for where we go next. Okay. So again, big picture of what we've done here. Grand mean centering. Level 1 predictors are still going to contain level 1 and level 2 variability. It only becomes a unique level 1 predictor after the level 2 partition of the variable is included in the model. Grand mean centering is going to give us within group and contextual effects directly. It is not going to give us the between group effects, so we have to ask for it. And I've shown you how to do that in LinCom estimate test and contrast 1D statements. Okay. Random effects of level 1 person level predictors. So there are 2 questions specific to any level 1 predictor. Is there an effect on average? Remember that average effect is going to be captured by its fixed effect. That fixed effect is assumed to apply equally to every single person or state in our sample of data. So is there an effect on average? If there is or is not an effect on average, does that average effect adequately describe every group in the sample? Do groups need their own slope for that predictor? The way we quantify whether there's between group differences in the effect of a predictor is via random slope variance, conceptually similar to random intercept variance. Only instead of with the random intercept, we were quantifying like amount of the predictor. Now we're talking about the size of the effect. So does that fixed effect adequately describe everybody in the sample? We can view this with pictures. So if our outcome is on the y-axis and our predictor is on the x-axis, let's say our outcome is disability, our predictor is level 1 age. The thick black line is going to describe our fixed effect. So on average, for every 1 unit older a person is, the outcome is not changing at all. So this is fully flat slope. There's nothing going on. The 4 thin black lines represent the age slopes for 4 groups. So you can see here that there is a random intercept variance. Some groups have more of the outcome than other groups. But on average, the change or the difference in the outcome for being 1 year older for each group is adequately described by that fixed effect, right? The slopes for each group here are parallel to the fixed effect slope. If we had a statistically significant fixed effect of age, so people who are older average higher disability. Again, we can see that the slopes are here, and this fixed slope indicated by the thick black line adequately describes each one of these 4 groups. So the effect of age within each group is similar to the fixed effect that describes everybody. So this would not be a random effect either. Okay? There are no between state differences in the effect of age because that fixed effect adequately describes all the groups. In contrast, if we had a fixed effect of 0, but that fixed effect of age is only 0 because some groups actually have a positive age slope and some groups actually have a negative age slope, so they cancel each other out. This is critically important. So our fixed effect would come back as not statistically significant, but clearly there's between group differences in the effect of that predictor. And so what that means is if you're thinking about your multi-level model and quantifying between group differences, it is not enough to say that there's just no difference on average. There's no fixed effect of that predictor because that fixed effect could be 0 because the groups are canceling each other out. So my suggestion is when you have level 1 predictors, test the fixed effect and then test for the random effect, regardless of the statistical significance of that fixed effect, because again, it could just be 0 because the groups are canceling themselves out. Here's an example of between group differences in the effect with a statistically significant fixed effect. So level 1 random effects are added to the model very similar to how we added the random intercept. So we're going to add basically age 65s in the model alongside state mean age. Again, we're still within grand mean centering here. The new effect we've added here is U1. So again, U's represent random effects. The 1 is indicating that we're talking about the slope for age. So thinking back B1, you can see it's for age. Okay. So the residual is the person's specific deviation from their group's predicted outcome. That's still the exact same. Variance is still the residual variance. The fixed intercept is the predicted outcome when both age and state mean age equals 0. So basically for a person who's 65 who lives in a state in which the average age is 65. Level 1 effects still interpreted the same, unique within group effect after controlling for state mean age. This is still the contextual effect, so it's the unique between group effect after controlling for a person's age. The random intercept is the group specific deviation specifically at age 65. So this random intercept variance now, once you've included a random slope, is now going to shift around. It's going to shift around because it's conditional on the predictor with the random slope equaling 0. So just like the fixed intercept is conditional on all predictors equaling 0, the random intercept is conditional on the predictors that include random slopes equaling 0. So that's why it's for someone who is 65 years of age. What that also means is that if you're thinking about pseudo R-square, when you add random slopes to your model, your pseudo R-square values need to start resetting because you've now shifted around this random intercept variance and you've added a new variance component. So you basically start over. And I'll show you that in the example. Okay. The random slope is the random within group age slope. So it's the group specific deviation from that fixed effect. I mentioned earlier, random effect variances are included in something called the G matrix. That G matrix is generally considered to be unstructured. Unstructured means you're estimating every variance and covariance. So there is going to be a covariance between the random intercept and a random slope. That covariance can be converted to a correlation. A positive correlation would mean that groups with higher random intercepts also had higher random slopes. A negative correlation would indicate that groups with higher random intercepts have lower random slopes. So this is equation that can be tough to digest, no doubt about it. So here's a picture. Let's consider level 1 age. We're going to go from 63, 64, 65, 66. So black line represents the average effect, the fixed effect. The blue line represents one group's effect, so for a single group. So our fixed intercept here is an outcome of 10. For every, the deviation, the random intercept here, we centered at 63 years of age. Actually, this one group at age 63 has a random intercept of -4. So they have a value that is 4 units lower than their than the fixed effect. For every 1 unit increase in age, the outcome is increasing by about 6. So this is the fixed age slope. But you can see here that the slope for this group is steeper. And the random slope represents the deviation from fixed. So the random slope then for this group is actually 2. So for every 1 unit increase in age for this group, we saw an 8-point increase in the outcome. The difference between 8 and 6 is 2. So the random slope would be a value of 2. Residual values still represent the same thing. Deviations from their own group's mean. Okay. I mentioned earlier that random effects end up in the G matrix. So now we have an actual matrix, not just a scalar. So we have our random intercept variance, our random slope variance, and then the covariance between these two. The addition of new random effects is tested via likelihood ratio test, so model comparison. This is why I focused on the -2 log likelihood from model 3B, because that's our starting point. We are going to add a random age slope in model 3C, and we're going to test whether it fits better than model 3B. So the random intercept model included one random effect variance. The random age slope model included 2 random effect variances and the covariances. So the degrees of freedom between these two comparison models is 2. Again, if you're estimating in REML, make sure that basically model 3B has the exact same predictor variables, fixed effects, as your comparison model with your random effects. Just like we had done before, we can quantify random slope variances in terms of the actual outcome using that 95% random effects confidence interval. And then after, I mentioned this earlier, after including your random slopes, we have to reset our pseudo R-square calculations. And again, that's because random slopes are also partitioned out of residual variance. So residual variance now is going to decrease. Not decrease because we explained it, decrease because we've partitioned out another level 2 variance component from that. The random intercept is also going to change because it's conditional on the 0 value for the predictor with the random slope, like we saw earlier. So this is where we were at previously. We had our regression model. We basically parsed out between group differences from residual or from within group differences. Random effects are further partitioned out of residual variance. So now we're going to dip into residual variance again to grab our random slope variances. So we have our residual variance at level 1. We have our level 2 random intercept variance, and we have our level 2 random slope variance and the covariance between them. Okay. So again, testing these effects require likelihood ratio test via model comparison via likelihood ratio test. Okay. Real quick, a little bit of commentary on random effects, and I need you to suspend your disbelief for a minute. If you just breathe in and exhale, we can do this, okay? We are in grand mean centering. Grand mean centering, again, that level 1 predictor, included level 1 and level 2 variability. In the model for the means, we deconflated that to provide unique effects by including that state mean age variable. However, when we include our level 1 age predictor as a random effect as well, that is still a convergence effect. Okay, so even though we disaggregated on the fixed effect sides by including state mean age, the age variable, the level 1 age variable as a random effect still contains level 1 and level 2 variability within it. Okay, I know this because there is forthcoming methods literature to support this. They have algebra, they have plenty of examples with simulations. Okay, this issue is conceptually identical to the fixed effects. So what you technically need to do if you're in grand mean centering and your level 1 predictor has a non-zero ICC, indicating that that level 1 predictor contains level 2 variability as well, you also need to include its level 2 portion as a random effect. This means we would include state mean age 65 as a random effect as well. Of course, in a 2-level model, there's no higher level, there's no third level for that level 2 state mean age variable to vary across. I've never actually got this to estimate. I've tried many times on many data sets and it has never estimated. We're going to try to do it in the example and it didn't estimate there either. But again, conceptually identical to convergence effects for fixed effects, we can get convergence effects for the random effects as well. Okay. So technically you need to include both pieces as random effects. That said, it is never estimated for me, and I've seen a lot of data sets. All right, that was a lot of words. That was pictures. Some of you undoubtedly are feeling a bit lost. If I could see your faces, I would know that to be true. An example should help clear some of this up. So let's go back to the grand mean centering and look at models 3C and 3D. So again, The way we test the inclusion of new random effects is via likelihood ratio test. So this value, 131,07602, if I go into my Excel spreadsheet, 131,0760, I left off the 0.2. No, I didn't, it's up here. But this is going to be our comparison model, model 3B. So if I scroll down, again, all interpretations of fixed effects provided. We're going to add our level 1 respondent, random level 1 respondent age. And the way we've done that is just add that random effect for the age predictor. It becomes multiplicative here. That's how we end up with heterogeneous slopes. In the software, though, still basing this off model 3B, in Stata, we're now adding age P65 after the double pipe. Okay. The other thing that we've done is now we're adding an ESTAT option for random effect covariance. That's going to give us an unstructured covariance matrix, the G matrix, basically. We're also going to store the estimates from this model. So one of the nice things we can do in Stata is we can store estimates from this model and compare them to the previous model that we stored above. So if I scroll up here, I'm hoping this code is there. Right here. We had stored model 3B. And basically what we're storing is this information, -2 log likelihood. So we can compare directly, and then we can use the LR test option to compare. So no Excel, no calculator needed, no calculating degrees of freedom. It's going to do this for us. Not so true in SAS and SPSS. So the only thing we've done in SAS is we've added HP65 to the random statement. Same thing with SPSS. In R, we have now created a linear equation. So we have random intercept plus random age slope. Again, all of that showing the nesting of people within states. We can use the R ANOVA option to test whether the inclusion of our random slope and the covariance between the random intercepts and random slopes improved model fit. The hiccup here is this model didn't estimate in R, and I don't really know why. I thought that was weird. So basically, if you were estimating this and the model blew up as it would in R, basically you would have to say that there was no random slope variation, right? The model didn't converge, so there was no random slope variation there. So you would remove that effect and move forward. It did, however, estimate in Stata. And so where our focus is going to be is on these random effects parameters, particularly the random intercept variance, the random slope variance, and the covariance between the random intercepts and the random slopes. Okay. Whenever we've added new random effects, it'll give us values. We can test directly whether they were statistically significant, which we'll do here in a second. But what else we can do is we can actually put that variance estimate on the scale of the disability outcome using our random effects confidence interval. So our random age slope variance was 0.0000375, so very small. We can take our fixed effect for age, so 0.011329, plus or minus 1.96 times the square root of that random intercept variance. And so 95% of our states are expected to have a within group age effect that ranges between 0.008 and 0.015. So 95% of those states. We could do the exact same thing for the random intercept variance. And I've done that here. So here's our random slope variance. Here's our random intercept variance. So 95% of states now are expected to have random intercepts between 1.85 and 2.089. Again, this is conditional on age 65 being 0. So basically for somebody who's 65 years of age. So we can do that. That's useful for interpretation purposes. The next question we have actually is whether including the random age slope improved model fit. The way we test that is via likelihood ratio test. So here again is our model 3B, -2 log likelihood. If we take our -2 log likelihood from model 3C, we can see that it's come down. Anytime you add predictor variables, your -2 log likelihood is going to decrease. Or sorry, anytime you've added parameters, your -2 log likelihood is going to decrease. How much did it decrease? 137.2. We've added 2 variance components. Again, random slope and the covariance, or degrees of freedom, are 2. P-value is less than 0.001. What that means is that model 3C with the random age slope, the random level 1 age slope, fits statistically better than the model without it, indicating that states need their own age slope. There are between state differences in the effective age. The likelihood, so again, we can do this by hand, and that's all fine and dandy. And I've done it again here as well. Done it here as well. Stata will pump it out directly for you. We get 137.11, again, within rounding error. P-values can't be 0, P is less than 0.05. Both of these, again, telling you the same story as they should. There is statistically significant between state differences in the effective age. How big are these differences? Well, 95% of them are between 0.008 and 0.015. So, again, suspending disbelief, adding random level 2 respondent age to the model. So we're going to take SM age 65 and we're going to dump it after the double pipe in Stata. We're going to put it on the random statement in SPSS and SAS, and we're going to put it on the linear equation for the random effects in R. It didn't estimate. Like I said earlier, I've never had this estimate, but again, the methods literature is there supporting that this is actually a thing. So for all of our models going forward, though, because this model didn't estimate, I'm going to exclude this because, again, I need models to estimate for the example, right? Okay. We're doing it, moving right along. Well, here, let me ask one more time now. Now we're an hour past where we were previously. Do you need a 5-minute break or do you want to keep going? We have an hour and 10 minutes left. Again, you can put in the chat, break, please. Yes, okay. First one, yes, that was a lot. That was super heavy. And that's really where a lot of the capacity starts to go by the wayside there. So let's take a break. Let's decompress for 5 minutes and come back at 3:55 Eastern.